screen. Okay. There we go. Extend monitor. Let's see where it goes. This one over there. It's not sharing. Reshare. Okay, so our available dates are 2 on the 22nd of February. My cables is not plugged in. Cable. Mirror. Okay. So that being said, I'm going to move this off to the side. 1, 2, 3, 4. Okay, so I don't have to open the chat. Okay, so the 22nd, 2-22. James.
Yeah, Mauricio.
Mauricio. MAU. Okay. And then 2-24, that's the Thursday. Yeah, Thursday after that. Okay, it's more than a week. So, Scott. We need one more slot that day. The next one is going to be on March 1st. Yeah, that sounds right. March 1st, and then March 3rd is the next one.
That could be March 1st.
Okay. Ruben and?
Aman. Our topic is related to 1, 3.
Okay.
So, me and mine and Mohammed topic would be on the same,
okay.
Same thing. So, can we schedule on the same day?
Is that okay? Do you want to go on the 3rd then?
I have to do the 1st to the 3rd.
Okay. Yep, you can do the 3rd.
Yeah.
Okay, well, do we have anybody for the 24th? Because Scott only has, there's only one Scott presentation on the 24th. Okay, let's do both of those on the 1st then, and we'll just do 2 on the 3rd. Does that sound good? So, Mohammed.
Do we bring a laptop or do you just bring a PowerPoint?
You can bring it on a thumb drive and use the computer here. If you have animations or something like that, you might want to bring your own computer. But if it's just PowerPoint presentation, it's going to be good. Name?
Amar Danish,
AD. Okay. And so that's on the 1st, and then the last 2 are on the 3rd. Ruben Jacob. All right, I will type that up and email that out to make sure everybody got that, okay? And if you have your title, I'd like your title or at least your topic a couple days before so I can send it out to everybody, okay? All right, great. So let's get back to sharing my screen.
Yep, right? So we'll do like a first round presentation and another one. Right?
Correct. Correct. The other one is a literature review.
Also presenting on literature.
And so it technically is a written text.
Oh, so there's just one presentation.
One presentation
One review.
right now, one literature review, critical review, a midterm with the take-home portion and an in-class portion. The final is take-home.
So we're not presenting on the review.
Correct.
Okay.
For the in-class question, like you have said that you will be asking something that you can remember, like the definition, something like that. When you will ask something that is the slides or what you speak? Because it's very
It-
difficult over that.
Everything will have been represented visually on a slide. Okay? If I didn't draw attention to it on the slide and it's somewhere buried in the book, that's me. I wanted to draw your attention to the cool stuff. And so if it's on a slide, you know, if a picture's on a slide and you want to go back and say, oh, that was high density polyethylene, that's good. But if it wasn't on a slide, don't worry about reading the rest.
Oh, thank you.
For the presentation, do you most your expectation just focusing some points, some experimental studies like mechanical, or can we do an overview like physical properties, mechanical, and then maybe technological properties?
Your choice. I would prefer it a type of topic like electrical or mechanical. And I would prefer you have the 5 papers you use either be doing different processes or doing all the same processes to getting different results. I want you to kind of weave together, hey, these groups, hopefully all doing good work, hey, got different results. Why? And then we get to talk about why. Does that make sense?
For example, if I'm doing like on nanomaterials on feet, how you incorporate them, for example, air spray them, or you absorb your ingredients in the solution containing the nanosilica, and there are a bunch of other processes as well. So I want to study on how they affect the microstructure, leading to enhance the mechanical properties, and why they are showing different results on the physical process. Good.
That's perfect. That's exactly. You know, it's like, you know, we did a pre-wet slurry. We did just during mix. We didn't do any pre-treatment on anything, and these were our results.
And like if I'm working on flammability
Uh-huh.
and you can accomplish flammability using different types of added materials or fillers, or are you talking about multiple fillers?
Depends if it's like a class of filler. So your different fillers do different things, right? Some of them are cooling agents, some of them are charting agents, whatever. If you pick a class, then it's just different processes or different polymers. You can even do the same filler with different polymers. See what the different effects are.
Because I was trying to focus it all on the DEL standard, and then how to accomplish that, say V0,
V0.
and then just like what types of fillers.
I think we explained to everybody what the UL standard is. Behind it, V0. So we actually do the V0 over in my lab, like probably one of our materials. So. All right, great questions. I think we're getting really close to some good talks. So let me get back to what I was going to talk about today. And it is hidden under here. So we're going to talk about mechanical properties. It's in the book. It's I think chapter 6-ish in the book, and it's some of the stuff from there, but some of the stuff I wanted to talk about included types of analysis, valid analysis, and some ways of thinking about your combination between your polymer and your filler material. So some of the words we're going to see, especially in mechanical, is tensile modulus, tensile strength. That's the most important thing. That unless you're doing films that have to be pulled through a machine under certain tensile strength, that might not be the best test to do. And so let's look at some of the other tests to do and see what they're valid. And you'll see that some things will help one and hurt another. And some things will hurt all of them, depending on what you have. So I wanted to go through those and the differences between the modulus strength and elongation, particularly, and then look at flexural, which is usually done on the same machine, but it's a really different thing. And then I wanted to talk about crete because a lot of people don't talk about crete, and it's actually very important for long-term use. I did a project for Scotland Oil, and that is like their #1 problem right now. It's crete because the seawater is 4 degrees C, the pipeline is 60 degrees C, and that just causes all sorts of havoc. And then I also want to talk about impact strength because there's a couple different ways of looking at impact strength, well, measuring it. And then there's a couple different ways of improving it. And we'll see that how some things don't improve it and some things will. Okay. So that being said, I wanted to start with the equipment for tensile data. You might have all seen this, but I think it's important that you see that, you know, they have basically your sample is put between the load cell, which measures the force, And then this measurement is your strain. But we also have a separate thing called an extensometer. Because just the lapse of where your jaws go can falsely give you an elongation. So we want to see where this actual extensometer gives us the actual elongation. So you can think of it as stress, strain, and elongation are the three different components. And then they're measured, of course, and stacked up on a computer. So that being said, with the polymer samples that we do, depending on how big a sample you have, you can go everywhere from thin film to dog bone. And we had a big injection molder over at Star Park where we could do nanocomposites through this twin screw extruder and pump out like 50 dog bones in like an hour. So we had lots of test data on this. So when we think about that, we want to look at the different kind of things we get from this data. And of course, the first thing we're going to get is modulus, okay? Because in theory, there's going to be a linear correlation between stress and strain initially before a plastic deformation. So before we get to that plastic deformation, which is this yield strength right here, then we can have this actually continue to go down or go up. If it goes up, it means it's maybe elongating something inside the sample, giving it a little more strength. If it's not, it could be just all slipping past each other. So whether this goes up or down actually tells you something about whether or not your material is well incorporated. Then you have what you call your ultimate strength. That's also where your polymer stops elongating in its normal regime. So that's technically your normal elongation. And everything, all the elongation after that is your unstable elongation. Unstable elongation is from until there you fracture. And then this fracture point is your ultimate elongation. So you actually have two zones for elongation. And if you just measured the stress curve here, it wouldn't give you a true number for percent elongation. And if you just measured it here, it wouldn't give you a true number. So a lot of times what they'll do is they'll give you plastic elongation versus ultimate. And so when we do that, we see that we also have another zone here. The ultimate strength is when, of course, polymer chains start slipping past each other. And when they're slipping past each other, they neck down, and then eventually you get a failure. Because remember, you're measuring, when you're measuring this, you're measuring it per unit area. So you're starting with a fixed area of approximately 2 to 3 millimeters. And then as it necks down, it's going to get small. So that's why before it necks is your ultimate strength, because you haven't changed your area yet. Then you change your area, and that's when it actually fails. Okay, so if we look at that again, what that kind of looks like is you have your dog on here. And again, if you just measure end to end for elongation, you're going to see something weird because before it starts necking, you actually have that ultimate strength in this area here before it starts necking. And if you just measure the elongation here, that's that plastic elongation here, normal elongation. And then as it necks, it can break anywhere in here, depending on what your defects might be. And again, it follows that same kind of curve here. This is our strain before the necking, and then our failure is our ultimate elongation. So, but tensile, which a lot of people run to immediately, say, oh, what's the temperature? What's the temperature? It's like, well, yeah, we measured it, but we've never used it for temperature before because it's a part of the window. Why do I need tensile strength? You really don't. You need like impact and flexural modulus and deflection temperature. Is it going to bow out at 40 degrees C in the summer? You need those kind of data. So you have to be careful about running to everybody wants tensile strength. Everybody gets tensile strength. But you can use the same machine to get flexural modulus. In fact, you can use a similar, most of the injection molding samples have usually 4 different things in it. One is a standard dog bone. It's an ASTM standard dog bone. Second one is a notched ISOD impact strength. Another one is an optical plate, which is a 3x3 optical plate. And then there's also straight pieces that you can also use for the flexural modulus. So if you have a kilo or two that you can put through an extrusion, you can get all this data. Now, in the case of flexural modulus, we're not worried about how hard we can pull it. We're worried about how much is going to be compressed in the top and how much is going to be under tension in the bottom. So you have this top part has to resist compression and the bottom part has to resist tension. And somewhere in the middle, you actually don't have much stress at all. So you have two different things going against each other. So that's why flexural modulus is sometimes harder to do, but much more important, because if you have an industrial material, if you have a building material, if you have a thing going in a tar, that number is actually more important a lot of times. And as long as your heat deflection temperature is above your intended use of temperature, which for most cars it's like 140 degrees Celsius. As long as it's above that, you should be okay. All right, questions about tensile, modulus, elongation, and flexural modulus. The stress strain curve on this is going to look the same. You're going to have a flat area where you measure your modulus, and then eventually it'll crack or fail in some way. It'll plastically deform. So the stress strain curve is very similar to this, but we don't have any elongation back up. You can also change the material by load cell. Let's say you have a really flexible material. You could change the spacing here and put a really light load cell on it. And so if you only have a 5-pound load cell, you just spread them 6 inches apart and you can get good flexible data. Or if you have a really, really tough material, you might want to put them very far apart and have a very big load cell. So the new concrete place testing they're putting out there, they probably are going to have very large distance between the two holders. A very large load cell to push down on it, because it's such a hard material, and you want this span to be high enough to get a statistically accurate modulus in your flexural range. Okay, so in contrast to flexural modulus, where there's nothing supporting it, we have the other thing that we call creep. In creep, what we have, is a couple different ways to do it. And if you have something that's going to be hanging on the wall, you want to do tension right here, where you want to put your sample in tension with a set load and measure the distance it moves over time. The usual thing is about 1,000 hours. It depends on the ASTM standard you want to do, but there's usually some constant weight, some constant temperature. You can actually do this at 3 different temperatures and look for a superposition curve where you're just looking for that distance change. Notice it's not the total distance change, it's the distance changed in that cross-sectional area you want to measure. Okay, when you neck down those dog bones, that cross-sectional area in the neck down region is the one you're measuring your strain unit area on. So you'll see that again. But let's say you want to put a nanocomposite under a generator. You don't want that creep number. You want this creep number. In fact, you don't care about tensile strength anymore. You want to know if it's going to deform over time at the operating temperature. So you put a relatively realistic load on your sample per unit area and measure that over unit time. Yes.
When you say realistic load, is this around the load that would be on it in practice, or should it be like an increased load to sort of like cut some time?
I'm going to have to use my engineering fun factor 1.5 times desired load. 1.5 times desired load over 1,000 hours. That's not a year.
Static load.
Huh?
It's static load too.
And that's static load, no vibration, no temperature fluctuation. 1.5 times desired load, 1,000 hours at maximum operating temperature would be a realistic number. So again, it's you can run off of your tensile, or this takes 100 hours, which 1,000 hours, which I want to say is like almost a little under 6 months. No, it's 4 months. About 4 months. You got to have a whole closet full of these things hanging there with all at the same load on there. Now, let's say you don't have, 1,000-pound generator to do the cross-sectional area. You make the sample smaller, put a smaller load on there. You get the same load per unit area, and you should get the same number.
equipment that will like test that long, or do you have to basically do it all manually?
My understanding is it's manual because you don't need to actually measure it every day.
Right.
Right. If you do it, if you're doing it more of a dynamic one where you're raising and lowering the temperature, those are usually like separate pieces of equipment, but those tend to be only like a week-long experience. My understanding is I've never done this not where I actually bought 10-pound weights and put marks literally on all of the things and measured them over time. And see where it has this like nice little line here over time?
It's not.
That's like 2 dots. And every 2 dots will make a line, right?
So you also kind of have to make sure that your sample's large enough that you're actually able to measure the difference. If it's too small, then you're
Right,
basically not human error, right?
right. So, I mean, like this is in a dog bone configuration. The distance usually is approximately 4 inches, depending on which dog bone size you have. It's 3 to 4 inches, and that's more than enough to measure the micron. A lot of this can also be done with video cameras now, where you just take a snapshot every day and you have to put it behind for the front. Like you can do pixel by pixel measure. In fact, the extensometer I showed you before, they used to be these little things that you clipped on, these 2 little like basically paper clips that you clip on and you measure their distance there. This is a video. It actually just does it by video screen capture, so that you can see that it's and again, pixel by pixel, frame by frame. And then you can hit the pixel where it hits the ultimate elongation and get your before, and then another picture when it does your failure. So, all right, questions on crete. Okay, so let's think of another kind of test we want to do for some kind of industrial process. We want our polymer to stay where we put it. We want our polymer to handle our fluctuation in temperature. So we need maybe know high temperature strength, low temperature strength. See if there's a possible failure mode if the grid fails in the middle of winter and all the power lines fall down for some reason. So we'll have to, look at but again, the first test most people do is tensile to see if it's improving or not. And that's good. It's a nice, good test, but it shouldn't be your last test. That's what I really want. Now, the reason I say this is because the next one we're going to talk about is impact. There's 2 primary types of impact. One is a notched impact that's supported on 2 sides, and that's called the charping impact. In the charping impact, it's mostly done with metals and ceramics, but it is done occasionally with polymers. And I believe there is one of these on campus. So in the charpy, what we're doing is we're putting a load, 2 pins, so that all of the load from the impact is centered on a defect. So all the load is centered on the defect, and it's looking for what happens here. Okay, just breaking or not breaking is not what we're looking for. We're looking at how it broke too. You can do an elastic deformation, you can do a brittle break, you can do a setting, you can do a, so if you're in your rubbery phase, it might just bend and tear out. If you're in your glassy phase, it'll have a clean break. If you're somewhere in between, you might have little fibrils or little tendrils. So you actually have to look at what the thing says.
So this is more like qualitative.
Well, you have a load plus there is a qualitative measure. You actually measure which kind of break it was.
So we do have now also a state-of-art device split Hawkins and high strain pressure bar.
Oh, really?
We also do the we look at the behavior of concrete and confined concrete under high strain with that device.
Isn't that the one that it has the
Strikes.
the weight and it strikes it and listens for the rebound?
It's for like,
So you want to talk about that?
it's for like important decent, important decent. And it's in the warehouse.
Wow.
It's a DPRL offsite.
Okay.
So we just got training.
Oh, cool. So yeah, I don't know much, but I just knew what it was. I've never used it. So I've seen it.
As I said, the concrete they do some aluminum and some polymers. That's also
It's a really high density polymer.
Yeah.
Carbon fiber stuff maybe. I know they use
We're
ultrasound kind
planning
of
to,
stuff.
we're planning to wrap it, the concrete
internal deflection.
You only tell us to do some collaboration.
Sounds good. I'm just working on flammable stuff right now.
You guys only got that training for that.
Cool. I know. Yeah. Maybe if we have 5 minutes, somebody can show me the video. Okay, so this is the first one. This is charping. This is where it's supported on both sides. We're putting all our force on this notch. The notches are defect. The more common one for polymers is what we.
How do you use the data? As you said, mostly we have the impact load, okay, like in industries where the load is fluctuating, okay. How you can correlate this figure on the right with the actual fluctuating load, like the load impact load will be constant, right?
No, we actually have two variables. We have two variables we can use: the separation point, the point here, separation point, and the weight of the hammer. The weight of the hammer is on a pendulum. It's going to be accelerated by gravity. But you change the weight of the hammer, you change the force hitting at the
I found that that's the dead load.
No, these hammers can be changed. Back here at Texas State, we have a 30-pound, 5-pound on not the Sharpie, on the ISO.
The size of the notch also.
The size, no, well, you don't change the size of the notch. No, the size of the notch does not change. It has to be less than 1/4 of the width of the tank.
Okay, sorry, let me rephrase that. But so it can be less than that, but when you still have it less, it affects your
You have to,
calculations, right?
no, you have, as long as you're keeping the ratio, you're accounting for X amount, this is cross-sectional area. You're just making sure it defects right where you want it to. If you still, the cross-sectional area is part of the calculation. So that way you can actually have a smaller size if you have to, but it's better to use because most labs will have a machine that notches. And so you'll pass the straight bars and then we'll notch the machine. It'll notch the machine in at a specific angle and depth. So we usually don't change the notch, but by changing the distance here in the hammer, you get as much of the full load through there. Again, if you have a really rubbery material, you want to have these notches closer together so it has less chance to do this. You're trying to get all the force to go through that little teeny section first. If these notches are too far apart, the tension and compression of the rest of the sample might come into play. So we want to eliminate that. Now, what's the difference between the tensile and the impact?
So one is the characteristic liquid load and one is the constant load.
Not exactly.
One's just a flaw, it's just a one.
What about the strength?
Strain rate. Strain rate. That's what I was hoping for.
Because cross is static.
Right, because in theory, if you change the weight of the hammer, the force is going to be the same at the top. Okay, so the thing that's happening here is the amount of time that it's hitting the sample. So you have the force over this cross-sectional area, but the rate is much, much higher. In a tensile tester, you can only go, maybe get, 30 millimeters a second. Here you're getting like 300 millimeters a second. It depends on the length of the rod as to its actual speed. So it's the rate of strain that changes. All right. So that brings us to the more common one for polymers. It's a very similar setup, but notice that the support is down here and we only support one side of the polymer. Okay. And so we're still also the notch is in the opposite direction. So instead of hitting it from this point here in the Sharpie where it's supported on these two sides, and you're trying to get it fractured from the backside through the notch, you're actually hitting it way up here, giving it a torsional component, and you're trying to make sure it starts at the notch and breaks from that. So you're actually inducing that load, inducing this defect on the actual impact side. So that's why it's kind of back. And plus, it's only loaded both sides. But again, you do the same thing to change the force there. You can change the height and or hammer weight to get a different strain rate. And that can back calculate to the cross-sectional areas, give you more impact. Okay. So they're a little different, but and And I think we have both on campus, but I know where this one is. All right, questions on impact. I'm going to talk about things that help impact and hurt impact later, but I wanted to show what the test was. Okay, so another thing we're going to see a lot in these materials, especially with platy things, is X-ray. And so I wanted to give a little teeny visual description of what the two X-ray types we typically see are. The first is small angle X-ray scattering. And the second is large angle X-ray scattering. The cool thing is you can use the same machine for both. You just move the sensor further away from the sample. So in the case of most of these things will look like this. You'll have a goniometer, your source coming through at some incident angle, and then coming to your detector. And by moving the detector, as you change this angle, you're getting the different layers, the different structures inside the column. Now, if you're looking at this versus the wide angle X-ray scattering versus the small X-ray scattering, you're cutting through it and seeing a different size regime. You're seeing all the same things that X-ray sees. It's density, it's about the Z number of the elements, the total density of the material. That gives you your shading regime. But one will give you really detailed information in the nanoscale, and one gives you a more macroscopic scale. So if we think about it, the small angle X-ray scattering tells us things in the nanometer range. So we can actually start looking at whether our particle is crystalline or not, whether our nanoparticle is crystalline or not. If our nanoparticle isn't crystalline, we're going to see a wide, broad absorption because of the scatter. If it is crystalline, we're going to start to see where the planes might be. Now, in the other one, we can have much larger agglomerates that will scatter in the wide angle scattering. So the wide agglomerates or multiple, like the difference between a clay tectoid is macroscopic greater than that 100 nanometer scale versus clay plates that are near each other. So you're going to see, ooh, tectoids, ooh, no tectoids, ooh, crystalline structure, ordered structure, or disordered structure. So that's what we're really looking for when we look at X-ray. We're looking for dispersion and order or disorder, depending on which one we want. And it's, again, it's a pretty easy tool to use once you get your safety training on it. And again, you can change the experiment from wide to narrow and get a lot of data. So I wanted to show a little bit about that. So what we can see here in this example is we can see that under 10 nanometers here, we can start to see clusters of little polymers and individual particles as they get bigger and bigger. We'll start to see those having these inflection points on our intensity. And then the larger agglomerates have to be done in a different method. Saxy actually stops around here. That's a different experiment. But the Waxy continues on way out here. And when we look at that, we can look at that super order on there. So in this case here, you can always tell whether it's wide angle or narrow angle by looking at the angles on the bottom of your thing here. Smaller the angle, more likely this small angle. Wider the angle, more likely the wide angle. But here what we're seeing is that by changing the direction of the sample, we're actually changing the direction of the sample. We're going from, oh, look, no disorder, I'm turning my sample. Oh, look, it's really ordered. And then I'm turning my sample, it's not. And then by the flipping it over, so what we see here is if we have this randomly displaced thing, we're going to get a slightly higher signal, but it's not going to be have these big peaks in it. Once you have this at the 90 degrees and 180 from the 90 to 70, you'll get the intensity of having those spacing you're seeing, the order you're seeing. Remember that order is on that 2 nanometer thickness scale. It's the plates that are all aligning, and that's what gives us our big scattering peaks that we see. All right, questions on small angle versus wide angle?
So just to, I guess, clarify, a fully exfoliated sample would be essentially there would be no peaks.
A fully exfoliated sample that is randomly oriented would have very few peaks that will have a broad line. But if there's any order at all, and there's tons of ways to induce order, you will start to see these. And if you have the tactoids that are partially intercalated, you're going to see a wider spacing than the clay by itself. All right. So then another thing we see a lot is SEM and TEM. And you probably all know this before, but I think it's important to note that SEM is wonderful and cheap nowadays. I actually worked for a company that had a benchtop SEM. We literally took chunks of aerogels, threw them in the thing, and did SEM. And that all comes from the fact that we're looking at reflection of our X-rays that go back onto the detectors. Now, you can either have a primary X-ray detector, or you can actually have photon electron detectors to detect metals. For $120,000, you can have one with both detectors, by the way. So the whole, it comes here, you get your X-rays, those are all focused. It's rastered across your surface, whatever hits your detector is what you see, okay? That works great, but sometimes you want to see through the sample. This is only going to see what's on the surface of that sample. If you're really lucky, you can etch away some a little bit later to maybe get the fiber to stick out somewhere, but that takes a long time. It messes up the pattern. So a lot of people go over the TEM. The problem with the TEM is that your sample can only be so thick, depending on density. The most average size for this is about 150 I should say, yeah, nanometers. 150 microns, I should say microns. You have to have it very thin so the X-rays can shoot through. Okay, and so instead of that, we have our sample actually up here after it's been pollinated and then focused on the detector down here. So our sample's in a different location. All the X-rays that go through are the ones we are sensing. It's not sensing anything that gets reflected off. Okay? So the big thing about SEM is it's great for big bulk samples. And if you have a tear or you want to look for a surface morphology. But if you want to actually look for distribution of things in there, you have to move to the TEM. And all the special processing that it involves.
Why did you want to look through the specimen?
Okay, let's say we made a polymer nanocomposite and sheared it really well. And we're going to take slices this way and slices this way. If we're looking through there, we can see plates are aligned with the X-ray or not with the X-ray based on their density.
Last general question: why we discover the materials like gold and palladium before the SEM?
You don't have to. In the old days, we did that because you want as many of the electrons to bounce off as possible. So if you, some of the sources used to be like 30,000 electron volts, which just basically eats through things that aren't metal. That's the first reason. Second reason is you want to dissipate the electronic charge that builds up on your sample too. So if you have a conductive grease or a semiconductive material, you don't need to put metal on there if you run it at a low enough voltage. Usually you can not run it if you run it under about 5,000 volts, you don't need to coat it. In fact, I think there's even environmental SEMs that are running closer to atmospheric temperature. You also don't need to coat it.
One more thing I just observed: when you cover with when you polish with gold or palladium, the carbon elements ratio comes always high, even if you don't have that much. Do you know any specific reason for that? Because it's so
More familiar with iridium. We used to use iridium because it's a little bit heavier. You can get a thinner layer on there. I don't know if it's inherently higher, why it would be inherently. Because in theory, it should be a solid metal target that's being ablated onto your sample. You should be doing it by vapor deposition, not by.
it's a known information. I don't know. Cementitious materials. People always say if you cover with palladium, you expect to see the higher carbon ratio, but I don't know.
I don't know the reason for that either. Interesting question. So I mean, so they both have their purpose, and TEM's a little more expensive, a little harder to prep. But once you've got, a lot of your data here, and you've got your X-ray data that says that, hey, I have order, you want to see what kind of order you have. So it's like that next test after your X-ray. All right. So I found this here and I've referenced it. I'm starting to reference all my pictures now. This is the difference between an SEM and a TEM, the same sections of a polymer nanocomposite. And in this particular one, they did it with these little sub 5 nanometer metal clusters. And then I don't know how they did this, but they gave a histogram of the particle size over a specific area they were searching. And if we look at the surface on this one right here, we have a nice bright metal surface. It's nice smooth texture. There's no polymer around that particle, right? Because we're seeing it from reflection. This is what that same particle looks like in the polymer matrix. Notice that the polymer matrix is here, and there is order in that material. So this might be a crystalline metal sphere. Okay, but it's really smooth also. These screws are smooth. Now, as we go over here, we're starting to get some surface morphology, and we're actually starting to see this texture is getting rougher. There's layers that are thicker than others. You're starting to see that surface roughness. You can see it really well in the SEM, but in TM, it's a texture, not that beautiful texture. Then you move over here, you get more surface roughness, and you can even see the surface roughness along the TEM. But you still see the crystalline order of the metal inside. And then when you get to the really, really rough particles, you can even see the divots in the TEM. As it's transiting through, this area has less metal than that, and this area has more metal. So I thought it was a really good comparison between TEM and SEM.
This is a close-up of one part, and
The TEMs are for sure, because these are 10 nanometers. So no, these are groups of, you're right, these are groups of particles, because 10 nanometers, they are 5 nanometer metal clusters. So yeah, these are groups of ones. I don't see these are attached to those, that's 1 micron. So those are clusters of metal spheres.
These clusters around that ball shaped thing.
So that would be a representative sample, not in a polymer matrix. This is the representative sample in the polymer. So that's probably what they looked like before they were processed. This is what they look like after.
It's SEM.
SEM. Okay, so now let's go back to comparing some data. Okay, so I said before, most people will run off and get the Tensile data, and they're going to throw a nanomaterial into it, and they're going to say, "Oh, it got better." Well, let's look at that a little more detail. What we have here is some glass fiber reinforced high density polyethylene, and let's look at the tensile strength and flexural modulus. Okay, so in tensile strength, we're going to pull it right here. So we have these nice platy montmorillonite with glass fiber in our system, and we see as we increase the loading of the clay in parts per 100 right here, we see that, oh, it's getting a little bit stronger. And if we include the top one, this is 0 glass fiber, 5, 10, and 15. This is no polymer, no clay, 2 parts per 100, 4 parts per 100, and 6 parts per 100. So you're like, okay, initially, just adding glass fiber increases the tensile strength. Okay, that's a good result, right? Well, okay, let's add our nanoclay to it. And, well, we see a moderate rise, but these are no bigger than these. They're not statistically different. So from that experiment, I would say, okay, we don't need to load this more than 4 parts per 100 clay because we're losing our benefit. And then say, well, okay, let's just look at the flexural, because that's different. We're doing tension and compression at the same time. So we see this is where we start with just the glass fiber filling. We see improvement, and then about the same, maybe a little. Now, if our use was flexural, we might want to load it just a little bit higher, just in case. But it's looking like this 4 parts per 100 nanoclay is actually what's helping. So then we say, oh, well, really, we're not going to use it for that. We're going to use it for parts on a train that get hit. So let's look at the impact strength. So here in the impact strength, we see that adding glass fiber decreases our impact strength. The material is becoming more brittle. And you're seeing that it's going down a little bit. It's less dramatic than in the tensile or the flexural, but it's doing here. So, is this a good filler for impact property application? No. It's great for a flexural or a tensile, but it's not good for that. So again, it's always important to know what your end use is, and what your end use parameters are to help you decide what you really want to add and don't add to your system. Okay. So those may or may not have been ordered. So does ordering your nanomaterial help your flexural and or compression modulus? Well, in an undrawn out film of polyvinyl difluoride, nice piezoelectric polymer there, it has very low modulus until you draw it out. But once you draw it out, at a ratio of 3 times, 5 times, and 7 times, our modulus goes up. Okay, so the neat polymer itself does improve its properties as we order. But if you look at the amount improvement, like having it as a nanocomposite, it's about 10% higher with a low loading of the nanocomposite. I want to say, I don't remember the exact number, but I think it's around 3 to 5, 8%. And they see, especially in 7, it's drawn out 7 here, much higher modulus. Okay. So then let's say, okay, well, maybe it's the polymer, the polyvinyl difluoride. Okay, so let's try with polypropylene. Do the same compound, do the same undrawn strength. You see both of them have still low modulus. And in all 3 cases, as we draw and order, the polymer, it increases in strength. But as we draw and order our nanocomposite as well, it increases even more. So 10% gain in modulus in 2 different polymer systems using the same drawing method. So that is with a phosphate modified single walled carbon nanotube.
When you say drawing method, can you remind me what that means? Like, are you talking about the processing, or is that?
Okay. Oh, so what we do is it takes it before it melts and pulls it 3 times its initial length, and then test it. Cool it down and test it. So drawing is you take it in a melt phase, you draw it up X number of times higher than it was. And so in theory, your cross-sectional area has shrunk. But that means everything's kind of lining up. Your polymers are lining up because it's looking past each other, and your elongated nanomaterials are lining up as well. Okay. So you're going to see this effect in long things like carbon nanotubes. But what about those little metal spheres?
Probably not as dramatic, but it could probably still.
If they were kind of like the nanowires, the nickel nanowires, that were all kind of cranky and hooky, probably. If they're just spheres that are independently kind of floating past each other, maybe not. Maybe not.
What is the, like in the section, graph on the right, it says, is it neat polypropylene?
Yeah, this is polypropylene, no nanomaterial in it. This is polypropylene with the modified carbon nanotube. So what we see here is if you look at the modulus and the ultimate strength here, the nanocomposite materials are 10 to 50% higher than the neat polymer by itself using the same process.
So they're just saying it's under more stress.
It's tougher, it has a higher modulus, and it has a higher ultimate rate. That's the, because you're thinking this is right where it breaks. So it actually has a higher ultimate rate.
How do you arrange the orientation of these nanomaterials?
If you look at the little thing right here, they take a elongated sample, warm it up, stretch it 3, 5, and 7 times, let it cool down. In that process, the cross-sectional area of your sample has decreased, and anything that is going to slip past each other is getting ordered, being like taking a rope that's all bundled up and kind of pulling it out. And then that's where we're getting the order. but we also changed our cross-sectional area. Now, most things that we have, films don't necessarily have to have a draw strength on them, but a lot of them do. They actually are drawn out during the process, and that increases their strength. But fibers, synthetic fibers almost always have to be drawn out 1, 10, 5, 100 times their initial length. Because once you draw your fibers out like that, they are just super crystalline.
You said that you have to draw them out twice the length, right?
It depends. Here they did 3, 5, and 7 times.
So it depends upon the length of the fiber that we're beginning with.
Right. So, for example, I think Capcom, no. Not Capcom,
Like the length should be so long that should be enough so that they can straighten up to the direction of the movement.
yeah, so that whatever bonding in between the polymers have is aligned as much as possible. I think nylon 6, typical draw ratio for that is between 10 and 20. So if it comes out of the extruder as X diameter at 1 meter, they're going to stretch it 20 times that, it's going to be much narrower. And that draw ratio, that percentage you draw from the original extruded to where it ends up, is the determining factor on it. Unless you pull too hard and start pulling too hard. So that's why those machines are automated. Okay, questions on that? So again, here, knowing that we have these really long, one long axis and 2 small axes right here, and knowing that we can probably, it looks like we can align that long axis just using this method. We don't have to use any other special putting them all down by itself. So we can use a bulk processing method to increase the ultimate strength of 2 different polymer materials with our one filter. So this is kind of a little bit more of how they do it. So they take the carbon nanotube and they modify it with these phosphate salts. One of the phosphate salts has fluorine on it to make it more compatible with the polyvinylidene dichloride. So fluorinated polymer, fluorinated functionalizing group on the carbon nanotube. Now on the polypropylene, they use a standard polyolefin chain, or just like a dodecile chain or whatever, and that's going to make it compatible with polypropylene. In both cases, they take the nanotube that's been modified for that particular polymer system and did a twin screw extrusion counter rotating to incorporate them. When they squirt out the nozzle, this is not a high enough shear to have them extremely ordered. They hopefully are really well mixed because we're using twin screw counter rotating extruder. But what that's going to give you is that's going to give you your nanocomposite as pellets. Then you're going to take those pellets and press them into a sample right here, and then you're going to heat the sample and pull it out a specific distance. That's how we get the draw ratio of 3 times the original, 5 times the original, or 7. Okay. So again, we're looking at a nice industrial size process. We can use phosphates pretty cheap, and getting to something that we can then order after it's been turned close to our finished good makes it a really good process. The expensive process is the last, or the first and the last one. Okay, questions on that? By the way, this paper has some of the best figures I've seen in a long time.
Object where in nature?
Polymer bulletin. Okay. So what they also ended up doing is looking at, was the polymer ordering or was the carbon nanotube ordering by looking at X-ray. So if we look at our X-ray here, these are actually X-rays. And what you're going to see is that the polymers, as they crystallize, as they're being drawn out, form these little platy lamellae, little crystals with these defect ranges or rubbery ranges. And we can see that the distance changes from about 11 nanometers to about 15 nanometers. Now, I don't know if that's big enough to fit one of those nanotubes in between those lamellae, but it did have an effect on the draw. So as we draw them out, we get this bigger distance between those rigid sections. Now remember, the rigid sections don't change much. The rubbery sections are the ones being elongated. And that's what we see in the change. And we see the same thing happen in the polypropylene. Starts a little bigger and gets a little bigger, but we have that same kind of concept that we have. Our polymer is also aligning, as well as our nanocomposite is also probably aligning in that length, probably axially to the lamella. Questions on that? So again, really pretty pictures in this article.
So it's drawn out 9 times as long as from the starting point.
Okay.
But you're saying that the distance between the two is only increased by that certain amount.
Right. So the lamella themselves have gotten slightly larger too, meaning that some of the rubbery polymer is turned into crystalline polymer, and some of the crystalline regimes are a little further apart. So you can almost imagine that you're like squeezing mortar in between the bricks in the thing as you're doing it. All right, other questions? Oh. Not going to go over the slide. Well, no problem. We got plenty of time. Okay, so let's, oh, isn't that the same slide? Yeah, that's the same slide. Stress strain, undrawn stress strain. Okay. Okay. So all of that up to that point was using one axis to draw us out and looking for a change in both the structure and ultimate properties of that. Can we do that with 2-directional ordering? So I said before, most films are usually stretched in one axis, and most fibers are usually stretched in one axis. But there's a really common polymer that's stretched in 2 axes. Biaxially oriented polypropylene or biaxially oriented polyethylene terephthalate. Okay. You will have immensely higher properties in biaxially oriented polymers. And so what we see there is instead of doing what we did in the first set where we heat it up to just below its melt temperature, but it goes flat and then it sets when you let go. In the case of biaxial, what we do is we stretch it in 2 directions at the same time. Okay, this can do a couple different things. If you have some clusters in your film and you are pulling in this direction and that direction at the same time, you could pull those clusters apart. When you're doing a melt phase, they can go back in to solution or anything. And in that pulling in 2 different directions, you're getting shear in 2 different directions. What do plating clays love? They love having that shear on them so they can touch the polymer and get the polymer ready. So if we look at the difference between biaxially at the same time, stretching both axes at the same time, and they have these special jigs for that, or stretching in one direction then another direction, you actually see a difference in strength. Okay. Stretch sheet, unstretched sheet. Okay, so in the TEM, we see in the unstretched sheet. So imagine we're casting something that's a foot by a foot. Okay, and now we're taking our TEM through there and we see, oh, we've got some saccharates here, a lot of plates are separated. That's okay. And then we take it and we do our biaxial stretch 3 times. So we take that 1 foot sheet and turn it into a meter square. Okay, so now we've sheared everything in 2 directions. And look what we see. We see that it's elongated. And this is sheared sheet, and this is in. This looks like one direction to me.
That's how
It looks like it's only in one direction. In 2 directions, I would have expected to be doing it. I'll double check that, but
it could be maybe the one direction first. The other one could be.
yeah. So it might be this portion of A, not the biaxially oriented. It's really hard to do biaxially oriented because you have to have a machine that has pins on this side and pins on this side, and they have to stretch out at the same time. It's like 2 pentagram pentalooms, the thing that separate pins separately. So they might have actually done it this way, which is why I'll double check.
You said that if you will do the double on both sides at the same time, then it will have a different strength by doing it separately. So
It should have-
everything.
It should have different order. But look at this strength here. What's the strength? The tensile strength in this direction is higher than the tensile strength in that direction. If you did it biaxially, in theory, these plates would be ordered in both directions, and you should have the same tensile strength in both directions.
That would be good or not.
Depends on what you want. In something like biaxially ordered polypropylene, it is so much stronger that it's worth the extra.
From your experience, when you see the one on the C, and then, let's say 45 angle, where's the most strength? Is it perpendicular to the cellulose or fibers?
Interesting. It depends. It depends on the nature of the filler. In this case, we're using clays. Okay, and this one, the clays are actually on edge this way. So it's going to be everything that's in the elongated axis on the XY axis of the clay. That's going to seem to give you the strongest tensile strength. But flexural is going to be across that grain, and permeation is going to be across that. Now, if these were fibers, then all we see is our improvement in tensile, almost no flexural improvement because fibers are thin. They don't help with as much of the flexural. That makes sense? Yes. So then we see that this is actually water vapor transition data that I'll come back to. But if we look at just tensile modulus, higher loading in clay and more elongation equals higher tensile modulus, which is what we anticipate. All right, let's see. So that's 2-axis. What about changing it? This is a weird experiment. We're going to use 3D printing in melted phase to change the axis of orientation as we process the material. Very clever idea. I love this idea. So what we have here is that if we have a nice 3D printer and we have enough shear in our nozzle to get a little bit of order here, we can then, by directionally controlling the direction of where we're moving it, we should get alignment this direction, and that direction, wherever we want to go. Alignment in a circle, right? And so if we look at what they did, they ended up with one that was 100% parallel with the dog bone sample that they're going to test. Okay? So they added one that was 45% off axis, 40 degrees off axis, and then one perpendicular. Empirically, if these are plates or fibers, we would think that the uniaxial one off the top should be the strongest. This one should be moderate, and this one should have no effect at all because they're going in the wrong direction, right? So, and then they of course did one where they just popped a whole bunch down and didn't have. So what happened? Well, if we look at the data, right here we get some interesting stuff. The modulus didn't change. The pure polymer itself is weaker than all of the composites. Okay, the one that's 100 that's parallel is the highest ultimate strength, but the modulus is the same. The one that's perpendicular 90 degrees was in the middle. I don't know how to explain that one. And then the one that was askew 45 degrees was the weakest. Almost like those things were trying to create a shear plane across that diagonal. So, can you do these different things? Yes. Does it affect your properties? Yes. Okay. Now, yeah, the other figure is tangential modulus, which is not very easy to. Okay, so the last example. No, I have one more. Yeah, actually, I want to skip that one for right now. I want to do this one. Okay. In this one right here, they were doing a polymer nanocomposite. I want to say it's nylon 6, and they have nanodiamonds. Okay, nanodiamonds are nice spherical hard particles, very good density, very good heat transfer, very good heat. And they were doing it by extrusion systems where they do the normal melt blending here. And then, you know, they were going, yeah, this dispersion's okay. We see some of the larger particles, some of the smaller particles. It's okay distributed. But then they had a problem in the machine. And the unit was doing what we call spurt conditions on an extruder. And in the spurt conditions, they found out that they had much better dispersion. Okay, so in an extruder, you typically run at a fixed temperature, a fixed speed, and the stuff going in, the stuff coming out all go at the same rate. So you think of the pressure going into your extruder, it's very low at the beginning, then it starts melting and mixing, it starts rising, and then you start necking it down to where it's about to come out of the fiber guide, and that's where it's its highest pressure. And as soon as it gets out of that nozzle, boom, it drops in pressure, right? So you're looking at increasing shear all the way to the die end and then it stops. Okay, and then if you're drawing out, there's a little, that's a secondary shear effect, but that we're just talking about the pressure. So in spurt conditions, what you do is you actually have a problem in your flow. You have a problem in your melt flow. Most of the time, you're gonna have this nice smooth shear stress in your system. This is going from usually your high temperature zone. Then you can have a second zone here where it's just too liquid when it comes out. It doesn't form any big fibers, but you have this area of instability here. It wants to just melt out of the end of it, but it wants to stay going forward. And so what happens is you end up getting a difference in pressure as it comes out. So this is its normal pressure here, and then it rises and then comes down, rises and comes down, rises and comes down. This is spurt mode. In spurt mode, they had better shear of small particles at the very end of their process. Very good dispersion. And what they saw was that it went from having large diamond clusters. Only because of this bad extrusion did they see very good incorporation. So what do we get from this that they really need instead of this spurt mode? What do they need to make better nanocomposites from this system? Variable pressure, not that well, increased pressure. But if we look at this, this is pressure, and so as pressure rises and drops, shear is increasing as well. So what they probably need is to change the blades so there's more shear running at a lower temperature, so that they can get it to stay in this nice sharp skin or smooth mode. You want to have that better flow with a higher shear. Apparently, this little bit of extra shear in the systems will give them a better dispersion. So that I thought that was a kind of an interesting way to do it as well. Okay. All right. So the last thing I want to talk about, I have 5 minutes, is impact strength. Okay. So impact strength is different, right? Because we have a different amount of force happening at a different amount of time, right? And so what we're looking at is different things are going to help us. Brittleness does not help us in an impact situation. Okay, because in a brittle material, cracks propagate faster because there's less resistance to crack propagate. Okay, rubbery materials don't fracture, they rebound because they can absorb, disperse, and elastically give back some of that energy. Okay. So how can we incorporate this with a nanoparticle? Okay. So let's think about this, saying, oh, okay, well, just adding silica to these things makes them more brittle. Okay. We have the polymer kind of stick into the particle is brittle itself. Okay, that makes sense. The impact strength is going to go down as we do that. So how can we kind of fool our system with a nanoparticle to make it not do that? Okay. Well, it turns out they tried 3 different fillers in this one right here. They tried the neat polymer, which has a decent notched impact strength. They put a plating material one-dimensional big plates. They put a nanotube, two-dimensional, long aspect ratio, and a spherical powder. Not only that, a spherical soft powder. Okay, so what happens here? The plates just make it too brittle, and it goes down. The nanotubes make it a little brittle, but it doesn't go down as far. But look what happens with the calcium. The calcium here, it increases, and we can actually even use the calcium oxide treated system, those little soft particles on the outside of the nanotubes help impact strength. Why?
Because of the material they produce.
Because what?
Because of the material they produce, average shock absorption, something like that.
Not shock absorbance.
Is it like dislocation, essentially, when
That's
it's a
almost
spherical particle that kind of goes around it instead of?
Almost. It's very close. We're very close. We're doing a concept called rubber hardening, where you take something that absorbs the energy in the propagating crack. So yeah, you're saying.
That's what I was trying to get at.
Yeah. So imagine you have, in the classic case, it's a piece of epoxy and a rubber ball. And you start cracking your piece of epoxy until you get to a rubber ball. Rubber ball can disperse all that energy and it doesn't continue cracking. That's called rubber hardening. So we're doing this on a nano level by having a very soft calcium carbonate particle being able to absorb these cracks. And they're not even big cracks, they're nano cracks hitting nanoparticles. How much force do you think you're dispersing? Right? So you're going to be able to disperse, so as your crack's propagating, it's going to hit something, and then it's going to absorb that energy, break that little teeny particle apart, and guess what? The rest of your matrix is still in. Right? So that's one way to do toughening of our materials, is to do spherical particles that absorb energy. Okay, and that's all I have for today. So I will give another thing on. Oops, sorry, let me quit recording.